Now next, I've talked so much about your fairing and the offsets. Now the methodical series, sometimes we follow the offsets given by methodical series. Now this series of ships, normally we have what is called series 60 ship. Series 60 Series 60 ships have been tested for resistance in a towing tank, and the towing tank has supplied faired offsets. Faired offsets supplied by towing tank. Now, sometimes, normally the shipyards, they can take recourse to the Series 60 lines. Of course, now Series 60 has become quite old, but these are proven lines from the point of view of resistance. That is why if one makes a bulk carrier to Series 60, then the builder and the owner is assured of the speed. It is called Series 60 lines, and you can have various hull forms following a particular series. If you just give the input, say input to this Series 60, you will find design charts. Of course, I don't have those data here. Design charts have inputs of, say, prismatic coefficient CP. I'll tell you what is this prismatic coefficient because lecture pertains to that. Then you have L by B ratio. Then the volumetric coefficient, or sometimes this is called volume coefficient, and LCB positions. So for different, the charts will, or the tables will give the different offsets for different values of CP, L by B ratio, volume coefficient, etc. For the ship, normally one has to build. So these are called methodical series. So methodical series, they supply the faired offsets straight away. But again, it has to be faired in the, I mean, you have to produce in the model of the full scale drawing. Now, there was an attempt to mathematically reproduce the water lines. Mathematical reproduction of water lines. Of course, this I am not going too much of detail, and sectional area curve. Now here, gentlemen, of course, this took place a long time back in 1915. This person is an admiral, Admiral D.W. Taylor. He proposed a carved line which will have some ship coefficients or coefficients of hull form characteristics. So he said that this curve, that is of the water lines and also the sectional area curve, they can follow a what is called equation like y. He said you can write in this form tx plus ax square plus bx cube, like this you can write a polynomial equation. Of course, now of course this method is quite advanced, called numerical production of ship lines by means of B splines, etc. Spline fitting has now come from this polynomial. So this was the earliest work, and he said that this polynomial you can write in terms of ship particulars. Say y, you can write as a coefficient called Cy plus PCP plus TCT plus alpha, like this you can write. Now see here the coefficients. Now this P is called the ship term, which is called water plane area coefficient. This same equation can be used for formulating your water lines as well as the sectional area curve. Now this is water plane area coefficient. This is if you want to draw a water line. Then P is a water plane area coefficient, and this P assumes the value of prismatic coefficient. I'll just now explain what are these coefficients. Prismatic coefficient in case of sectional area curve. Now next you can have T is another item we have got is T. The T is nothing but tangent or slope, tangent of curve at both, tangent of both waterline as well as sectional area curve. Tangent of curve you can write. And the last parameter is alpha. Alpha is second derivative of curve at amidships. So there are you see any mathematical curve should of which the ship lines is nothing but a smooth curve. It should have continuity. That means it should have a slope or gradual change in the slope. That means you should have dy by dx. And second derivative should be d square y by dx square. So wherever there is a change in the slope, you can find out this d square y by dx square. Otherwise, the slope will be dy by dx. So these are the mathematical definitions of the lines. Of course, now it has these polynomial equations. Now it has become much more advanced, and normally you try to find the ship lines to be made of these B splines, or sometimes you find cubic splines. These details, that is the polynomial equations and how to get these splines for your water lines in the forebody and the afterbody, these details are given in numerical methods in, I think, ship design by Professor Kuo. He has written a book on this, how to produce a mathematical hull form. So if the hull form is produced mathematically, then it is much more easier to fit the data in the computer, and you can get the faired hull. So the present practice is on this B spline, cubic spline, etc., and generation of the hull surface in patches. So actually, you will find these splines also will differ according to the position on the ship. The same spline will not be there for the forebody and aftbody. Aftbody will have different splines, and then how you merge the splines, etc. All this has come up in this spline fitting. So this brings us to the end of this lines fairing. Now coming to the coefficients, one has to make certain calculations from the lines. Now we are going to the calculations. This is called hull form coefficients or coefficients or form. Now these form coefficients, they are very important from the point of view of, first you calculate importance. Number one is calculation of buoyancy. Why? Because these forms, their ship is not a rectangular block. As you have seen in the lines, it is made of definite curvatures. So obviously it is not going to be a block. Now from this, by applying these form coefficients, you can calculate to the block, you can calculate your buoyancy. Next, what you can calculate is the center of buoyancy, which is given by the LCB position. LCB is nothing but longitudinal center of buoyancy. So these are the calculations one has to make from lines drawing. So unless you know the form coefficients, you cannot calculate buoyancy. LCB is nothing but the longitudinal moment of this buoyancy from either the midship or from any of the perpendiculars you can take. Next is another item which is called VCB, or the vertical center of buoyancy. You will find that this VCB is also very important from the stability of the ship. The stability of the ship in your mechanics of floating, in your subsequent class, you will find it is dependent on a parameter which is called the metacentric height. All of you, should have come across this GM calculation. And this VCB is important from the point of calculating this metacentric height. And normally if the G, or the center of gravity, goes beyond or approaches VCB, and GM falls below a certain level, then the ship can capsize. So from form coefficients you can calculate buoyancy, LCB, VCB, and what is other parameters that you can calculate is your resistance of ship. The form of the ship, which is governed, or which actually this is some mathematical information has to be obtained from the lines. Otherwise, you cannot do the calculations of buoyancy and center of buoyancy. In order to obtain that, we take recourse to these form coefficients. So resistance is also another factor which is governed by these form coefficients. Resistance, propulsion of course is dependent on resistance. We can write resistance and propulsion both. So these are the major parameters which can be calculated only after the form coefficients are known. Now what are these form coefficients? Now, after you have made, I think you may consult a number of journals and just have a look at the nature of these lines and sectional area curves. It will show you, it will give you a picture of the dimensions, the form of the ship. Ship form will be vastly different according to their function. And based on these forms, the form coefficients will be evaluated. So the first is the block coefficient. Now this block coefficient, this is important from the point of view of calculating displacement. So by Archimedes principle, I am not explaining again in detail, you find any floating body, a ship is nothing but a floating body, the weight is supported by the buoyancy, and the amount of buoyancy is given by the volume of water that the ship displaces or throws out for that particular draft. So this is the immersed draft. This you can calculate. That means the ship is nothing, that the weight of the ship that is acting through this point G will be supported by your water pressure, isn't it? And on the curved hull, the pressure also will be acting. So you can take the normally to the plate of the ship. So these components of pressure which are acting on the side shell, you can break it down into a vertical component and a horizontal component. Now these horizontal component will balance out for both on the sides of the hull, and this vertical component along with the pressure that is acting at the bottom will support the weight, and this weight you can find by is the volume that is displaced, that will be given by rho g multiplied by draft, rho gh multiplied by the area at the base. You take the horizontal area, so that will give you the your draft is this, you will get this area, and rho g if you multiply, you will get the volume that is displaced. So that is the Archimedes principle. Now this displacement you can calculate from this block coefficient. This is called CB, or coefficient of block. Now this block coefficient is a ratio of the underwater volume that the ship has displaced, that is given by this inverted delta, or nabla sometimes it is called, multiplied by the length, breadth, and the most important is the draft. So here delta you write is the volume of displacement. Normally displacement we mean that by in terms of weight, but volumetric displacement is denoted by lambda, and if you want to denote it by weight, that is multiplied by rho g, this will be displacement by weight. Now L is ship length. Now this length is little bit tricky. That means different persons, they use different lengths. This length normally you can take it as the length between perpendiculars, LBP. The normal practice is to take length as your LBP. But other persons, that the hydrodynamist will, he will not be convinced with the LBP, but he will be more interested on the length on the water line, or sometimes they call it the effective length that the ship has. LBP you take, I think that is the best, and B is the molded breadth. Yeah, B is the molded breadth at, not at any station but amidships. So actually, all these coefficients, it is better to base on some molded dimensions. And if you do not base, if you want to take the shell plating into account, then those are called extreme displacement, isn't it? There is a molded volume and extreme displacement, which extreme displacement will give you the volume of water displaced by the shell plating. And T, of course, is the molded draft, or sometimes this is also referred to as the mean molded draft. Mean is the mean of forward perpendicular and after perpendicular draft, that is called the mean draft. This mean draft normally you will find at midships. So this is your block coefficient, and block coefficient actually will tell you the kind of ship that one has designed. Now CB normally varies between as low as 0.36, 0.36. This is high speed ships. That is the normal, you will find the destroyer hull or the cruiser hull, they have very low block coefficient, and consequently if you have very low block coefficient, that means your volume of displacement is pretty low. The destroyer, for that matter, has very small amount of displacement because it is a high speed ship, and CB can also be as high as say 0.92. Of course, mostly I have come across CB of 0.885, and these are normally for tankers. Tankers, cargo ships will have around say 0.7. Normally 0.67 is for cargo ships. Container ships will be less, around 0.6. Container ships, because they move faster, say around, say nowadays container ship speed can be as high as 30 knots. So this is the range of CB. Next is the midship coefficient, or sometimes properly it is called midship area coefficient. So that is given by Cm. This is immersed area of midship section. you will find later on there is a relation between CB and CM. Immersed area of midship section divided by breadth multiplied by the draft. Yeah, the same B that you have taken for block coefficient. So here you will find this is midship area. So remember this, all this is the, we are bothered about the underwater volume of the ship, not the volume up to the main deck. Yeah, B is the molded breadth. Molded breadth. So here the ship is immersed to a particular draft, and this is the maximum breadth that midships. Of course, normally you will find at midship the side plating is vertical. When you have crossed the bilge, this is called the round portion is called the bilge, and here normally the bulk carriers are tankers. Of course, they are much more fuller. So this is your midship section area. You can write this as AM, and this is your breadth, that is B, and this is the draft. So this midship area shows the fullness of the form. If you have a higher mid immersed area, so then it will take like this. Now for high speed ships, you will find that the midship area is not very high, but block tankers etc. will have a high midship area coefficient. Now some in the range you can write CM. Normal ships is 0.75 to 0.995. Now this is for cargo ships. Cargo ships, tanker will be around 0.995. Tanker actually it is very easy to build because you can find the midship area section coefficient or the block coefficient is also very high. Normally it will be made of straight shell plating, excepting a little bit in the forward and aft region. And the other is 0.62 for high speed ships. Now, in this book, the go to the library, you will find a table is given for ship type and also this data on the coefficients. So that will tell you at a glance what is the nature of the ship. Another number 3 is your prismatic coefficient. So in short it is written as CP. Now CP is the volume of displacement. CP, why it is called a prism? It is prismatic means the ratio is the volume of displacement is given as a ratio of the volume of a prism with the midship section area. So this is called a prismatic coefficient. Now this Cp value is very important from the point of calculation of ship resistance. Important from resistance calculation, or rather resistance of ship. This is Cp. So Cp you can write, you can calculate immersed area of midship section from your midship area coefficient, that is your Cm. So here you simply write the underwater volume divided by length is your LBP. Normally that is better to take your LBP. And how much is the midship area? So this you multiplied by breadth multiplied by the draft multiplied by Cm, right? So this boils down to Cp is equals to so displacement divided by LBT is how much? Nothing but your block coefficient. So Cp is nothing but Cb divided by Cm. This is a very important relationship. Cp, should always remember, is a ratio of the block coefficient and the midship area coefficient. Cp is equal to Cb by Cm. There is another coefficient which is called the water plane area coefficient. It is normally written as Cw. So that gives the proportion of the water plane area. Now Cw is given as ratio of area of water plane. Now this divided by length multiplied by the breadth, but length here you take length of circumscribing rectangle. Length you can take as length of actually the definitions vary from according to the convenience. Some in the length that is given in the block coefficient, some will take as LBP, some as the load water line length, like that. But if you want to make the hydrostatic calculations, it is better to place on one single value. Length of circumscribing rectangle, and B is of course the maximum breadth. Maximum breadth on this circumscribing rectangle. Now CW varies between 0.65 to 0.95. So these are some of the important coefficients, and you can see all these coefficients, they vary by the draft. So the next teacher will talk about the hydrostatic tables, and he will talk about these coefficients which are calculated at a particular draft of the ship. So at this draft, at all these draft that, so at 1 meter water line, 2 meter water line, then you will get the low water line. You can calculate the displacement at all these water lines and the hull form coefficients, and these are plotted in a table called the hydrostatic tables. So normally you will find the draft is to be depicted on the vertical axis, and all these coefficients on the horizontal axis. Of course, there will be other parameters, coefficients, then your displacement, your LCV, all these are, you will find curves like this. This is your BMT, that is your metacentric curve, KML, etc. They will form what is called the hydrostatic curves. So that shows the variation in the draft, what are the values. Now the last coefficient which is important if one wants to know the vertical form of the ship, that is called vertical prismatic coefficient. Normally the CP, the normal CP that we have calculated, that is taken and the longitudinal dimension of the ship, that is immersed area multiplied by the prism. Consists of, prism means what? A solid object having uniform cross section area. Prism can be rectangular, can be square, or the sides can be polygon. The vertical sides can be a polygon, but in between there should not be any change in shape. So this is the longitudinal prismatic coefficient. Then you have the vertical prismatic coefficient. So that is given in terms of a parameter called CVP. So instead of taking the midship cross section area, you take the water plane area. The same volume, the displaced volume, you divide it by the water plane area multiplied by length into the breadth, that will give you the water plane area. Water plane area coefficient multiplied by length into breadth will give you the water plane area, and the prism will have a depth, that is the draft of the ship. So this is your vertical prismatic coefficient. It shows how much of the displacement, the proportion of the displacement with the vertical prism. So this is again displacement divided by length into breadth is again your what? Again it is block coefficient. So this is nothing but block coefficient divided by the water plane area coefficient. This is called the vertical prismatic coefficient. The other one that we have calculated is Cp is Cv divided by the midship area coefficient. Now, these coefficients are given, you will find in, if you want to draw the offsets from methodical series, they will give you these coefficients. That means the variation of these coefficients according to the LCB for various ships they have given in tabular form. And also from resistance you will find the residuary resistance curve. Ships normally, there are two types of resistance that will come. One is called the wave resistance or residuary resistance. The other is the frictional resistance. Now this wave resistance actually depends on the Cp value. So you will find the wave resistance or residual resistance curve which are based on various values of Cp. The last one is called the volumetric coefficient. So this is called Cv, vertical prismatic, yeah. So Cv is your displacement, volumetric displacement divided by L by 10. I don't know why they have made it L by 10, but I think to get some easy number.
It can be L into B into T also.
Yeah, that B into T is not given because L is cube. We are giving the cubic dimensions which is based on the length. Normally there is what is called another ratio which is called displacement length ratio. All these ratios are important from resistance calculation. This you come across when you study ship resistance. The displacement length ratio, this is the displacement in tons, the weight divided by L divided by 100 cube. So all these coefficients have been designed by a gentleman called, I think, Froude and Taylor. They worked on ship resistance. They wanted to present their data with these parameters. They are called resistance parameters. And the other ratios that are dimensional ratios, normally you will find the length divided by the breadth to be between 3.5, as low as 3.5 to 10. It can be as high as 10. Normal cargo ships you will find around 7. Then you will find length divided by draft. This will vary between 10 to 30. Then breadth divided by draft. This will vary from 1.8 to 5. These are the normal variations in these parameters. So by looking at the sectional area curve, one can make out whether it is a tanker or a high-speed ship. Normally you'll find the sectional area curve, it will look like this. This is for Cp is equal to 0.52, and tankers you will have a flatter region. Sorry, it will come in here. This CP value is around 0.80. This is sectional area and length. So an experienced naval architect, he can at a glance he can is able to tell you what is the type of ship by just looking at the hull form and sectional area. Now, since we have a few minutes, let me just tell you how to get these coefficients from sectional area. Now, given parameters are the total CP for full ship. This has been given to you, and LCB position. Now you can refer to a diagram which is given in this book. You find that LCB positions are given in a diagram like this. So this is your midship, and this is forward of midship. This region is forward of midship, and this is aft of midship. You have number of stations, say and the LCB is given as percent. If it is percentage of L forward of midship, then you consult the diagram on the right hand side, and if it is aft of midship, you refer to the diagram after the midship line. So LCB percentage of L, this is percentage of L aft of midship, and normally you'll find the LCB lying say between this, say this is 1% and the maximum will be say 5%, right? So 2, 3, 4, 5 is given here. Say similarly here also 5% will come, 0, 1%, and on the vertical axis you get your total CP value, and from this there are certain lines like this. If you refer to the table, so this is will give you CPF. These lines and the lines which are perpendicular will give you the CP aft values. So CP forward, CPF is prismatic coefficient forward. and CPA is prismatic coefficient aft. So given the ship, full ship CB and the LCB position, you can refer to this diagram whether your LCB is forward of midship or aft of midship, and here you have 1% to 5%. You can straight get a point, and here you can interpolate and find out what is the value of, say, CP forward from these lines, and from these lines you can calculate the CP aft. So both CP forward and CP aft can be calculated from this diagram. And once you have got the CP forward and aft values, then you can find out the section area. Again, anyway, since time is up, we cannot. So that gives you the section area forward and aft. So that brings us to the end of the lecture, and